And finally, the most important condition is the training inequality, and that the distance between x and y and z is at least the distance between x and z. Now, the most important definition of my talk is the following. Assume that we have two metric spaces M and N, and an embedding phi of M to N. Then we want to define how similar this embedding to an isometry. So the expansion of this embedding, or the Lipschitz constant of this embedding, equals to the maximum.
And what is F in the left side?
It's phi.
This
Point
is
worry.
phi.
No, another
the left side
alpha.
of the
It's phi. Okay.
next line.
It's phi 2.
Phi.
Yeah.
No,
On the left hand side.
Sorry. Phi is equal to the distance between the images. So we consider the ratio between the distances between the images of the points x and y, and the distance between x and y, and consider the maximum value of this ratio. So this is how much our map expands the distances. And the contraction of this map phi is equal to the inverse ratio, maximum over all pairs x and y, distance between x and y, and the distance between the images of x and y. So, and finally, the distortion of let me change phi is equal to the Lipschitz constant of phi times the Lipschitz constant of the inverse map. And this quantity, the distortion, says, in a sense, how far away from the isometry our map is. In particular, if we consider just the isometry map, then all these ratios are equal to 1 by the definition, so the distortion is equal to 1. Moreover, if our map just multiply all the distances by some constant, then, say, by lambda, then the Lipschitz constant is equal to lambda, and the inverse, the Lipschitz constant of the inverse map is equal to 1 over lambda, therefore the distortion is equal to 1. And of course, our goal is to construct embeddings that have small distortion. And in general, we will say that a metric space M embeds into M with distortion D if there exists a map from M to N such that the distortion of this map is at most D. So this is the definition that we will need. Now I'll try to explain why this definition is useful. First of all, one motivation comes from functional analysis, and which if you just want to classify metric spaces, then it's natural to say that metric spaces, arbitrary metric spaces, are similar to subspaces of some well-studied spaces like norm spaces. Also, using if we embed our metric space in some good metric space, we will be able to prove some structural theorems about our metric space. And finally, say we know that spaces L1 and L2 are different, but maybe we want to have a some quantitative number, what it means that they're different. So we want to say that every point in one space embed only this high distortion in the other space, and say that they're actually very different. But we are mostly interested in applications of this notion in computer science. And in computer science, there are two main applications. One of them is compact data representation, and these areas are very related to the nearest neighbor search problem. This is the problem Yury talked about 2 days ago. So the idea is the following. Say we have some family of objects, say web pages, and for every 2 web pages we have some similarity function. We know that some of them are similar, some of them are not. So if we have n objects, then we have roughly n squared pairwise distances. And it might be the case that computing these distances requires a lot of computation, so we want to store all the distances. And if we just store them as a matrix, then we need n squared space. Now assume that we know by some reason that our matrix space, so we have a matrix space on web pages, embeds into a low-dimensional space. Say it embeds into log n-dimensional space. Then we need just to store n log n numbers. So for every web page, we want to store the coordinates of this web page in this space, and then we can quickly, in log n time, compute the distance between two web pages. And moreover, this actually is very useful for constructing a fast nearest neighbor search algorithms. So in fact, it's much more useful than just reducing the space required to represent this data. But the area I'm most interested in is construction of approximation algorithms, and in this I will talk about applications of low distortion embeddings to approximation algorithm. But at first I will prove some theorems. First I will prove some theorems about metric embeddings, and then I will show applications of them to the sparsest cut problem. Let me give now. So the only examples I gave of embeddings are just isometry and scaling, and they have distortion 1. Let me give another example in which we have a non-trivial distortion. So
for example, what is the minimal distortion if you want to have a hemisphere sphere and you want to embed in a plane? Is it somehow evident or not?
If you have hemisphere,
just with
two-dimensional.
Two-dimensional with standard metric along the sphere.
I think it's just a projection, but for me it's important that it's constant.
No, projection is not because there are places when it's very sharp decline.
Right.
The slope is too much.
If you have infinite number of points on a hemisphere, then you cannot embed it isometrically.
Not isometrically, but imagine we look for an embedding of a hemisphere to a plane. Such maybe you translate into Russian what is hemisphere.
I don't know the answer. It's some constant.
No, it probably definitely should be some constant. We can just somehow make it from rubber and do something like
right.
But it's not easy to say which constant. So it's not something.
Probably it's not hard, but we are not interested in So it's not. We are interested mostly in asymptotical questions, and constants are the same as 1 for us.
Okay. Yeah.
So in general.
Okay, but it's not just I was wondering. It's not nothing. Not so. Just continue and follow.
Yeah. I think should. Yeah, I think this is the best embedding. Just consider. So we have hemisphere, and then consider the pole, and consider the radius and the angle. So for every point here, we have an angle and the distance from this pole, and then
just polar coordinates.
Polar coordinates, yes, the best one, right? But all the results I will present will have all notations, so we won't have any exact one. So one interesting example is the following: we have just a Hamming cube and dimensional, it's better actually, d-dimensional Hamming cube, and we can embed it into just the same d-dimensional Euclidean space equipped with the standard Euclidean distance. And here the distance is just Hamming distance, so the distance between 2 points is the number of coordinates in which they differ.
Isometrically?
No, it would be too much.
No, we can't embed it isometrically, but let's consider actually the identity embedding. Actually, this is the best embedding, but I don't prove it. So let's compute the distortion. So if we can write the distance between 2 points x and y as sum of
square root of d.
Yeah, it's square root d. So should I show it? Is it
yeah, definitely just between the most distant point we have d this way and square root of d this way. So probably it's
okay. So it's square root of d, and it's interesting. Right. So let's write it in the following way. We have square root of d, and d is equal to the logarithm of the number of points. So if n is the number of points, then this number is equal to the square root of log n.
And how this square root of d factors between the norm of phi and the norm of phi minus 1?
So
in one direction it's 1 and the other is square root of d.
Now let me first the first theorem. It's a very simple theorem, but it illustrates one map which is used for constructing almost all known embeddings. So, every metric space on n points embed isometrically into L infinity. And in fact, we need at most 10 dimensions.
So L infinity is just the maximal difference.
Right. So let's think of this space as a space of functions f.
The metric space itself, probably, yeah?
Yeah. Say from a metric space itself, or say from now set of numbers from 1 to n into R, and the distance between f and g is just equal to the maximum of fi minus gr. And this is...
And probably people already guessed what is the embedding, yeah? Or not? Which function corresponds to some point? Could you guess? No. We need the distance to have the distance between functions, just between distance between points. No, it's just a function distance to this point. If for each point we have a function which is distant to this point, we have exactly this, because triangle inequality plus.
Let me show the details. So let's enumerate actually for points x1, etc., xn for the principle of negation. And so for every point x, you map to the point which is distant from x to x1, distance from x to x2, etc., distance from x to xn. Now we need to show that this embedding doesn't increase distances. Look at 2 points x and y, then and look at the difference of
if we change x by at most 1, then all distances change by at most 1. Don't be so fast. Okay.
Why don't you just do it slowly?
Yeah.
Maybe I'll do this slowly.
Yeah.
So this is a simple example, but we will need the same idea in a more in another situation. So if we just compare coordinates of images of x and y, then we have distance of x between x and xi minus distance of x and yi.
Y and xi, I guess.
Y and xi. Now we apply the triangle inequality. The difference is at most distance between x and y. So, since the difference between in every coordinate between the image of x and the image of y is at most distance between x and y, we get that this map doesn't increase distances. Is it clear? Now, of course, if they denote, let's say, x is equal to some of this xi, x is equal to xi, then the difference at I coordinate, we have a different side here. And here, of course, this is just equal to 0, and this is just equal to the distance between x and y. So we found a coordinate in which the difference is equal to the distance. And this implies that our embedding is an isometry. Do you have any questions about this proof? So, this result...
So you call it isometry if the distortion is less than or equal to 1?
It's equal exactly to 1. So the distortion can never be less than 1. And I mean, it's an isometric embedding.
But what about the inverse mapping?
So here I prove that it doesn't increase the distances. So this means that the Lipschitz constant.
What is the question? I mean, in that formula, we have two factors, but one is equal to 1. In both cases, it's 1, because d of xi is equal to d of phi at x. It's isometric.
So
Exactly. It is isometric on our finite set. On our,
Yeah.
we just embedded our metric space, which we don't have anything else.
Yeah.
We embedded into the R. I see.
haven't
I see.
only this one.
Yeah.
And here, so here when we consider the inverse map, we consider it only restricted to the
I
image.
see. I see.
So this result, unfortunately, is not very useful. First of all, because the space L infinity is not very useful, and the second, because the number of coordinates is too high. So it is n, and there is no way to reduce this n. But here we use an idea. So our map, we map the point x to the distance from x to something, to some set. Actually, here we had a one-point set. To a set h1, the second coordinate was the distance from x to the set a2, etc. And we have many such sets.
Yury, so it's like idea of landmarks in the Andrew Goldberg talk. When we pre-compute the distances from every point in the map to a landmark.
Yes, somewhat similar. It resembles what idea like.
But here we have a set, so it's not exactly a landmark. One landmark.
Yeah. But what is the distance between points in the set?
So
Just the minimum.
Minimum, yeah. Mostly we will deal with finite sets that will be the minimum, and also in most examples, so m will be a finite set and n will be a normal space. And an embedding that is defined by a formula like this is called Trichet type embedding. And almost all embedding that I use are Trichet type embedding. So there are known results that in some cases it's not sufficient to consider only a Trichet type embedding. So in general, you cannot, for some spaces you need to consider other types of embeddings. Now let me prove the main theorem of my talk, Bourgain's theorem. What can I read?
I think the definition of metric space is not very
Right.
important now.
So the theorem is.
But I'm sorry, I missed what do you call Trichet type
So in
embedding?
Trichet type embedding, every coordinate is a distance from the point x to some set. So we produce some sets h1, etc., hm, and our embedding maps a point x to the vector like first coordinate of this vector equal to the distance from x to h1.
Yeah, so we have still the first inequality, but now it's quite possible that different points for bad occasion have very close distance, almost the same distance to all this set AI, and this is bad. But we hope to avoid this and so on.
You still use this distance, this infinity.
So I will use another distance.
Okay.
Here I use L infinity.
Yeah, in this whatever.
Here in this theorem, yeah, it's L infinity.
Yeah. No, but in this.
Trichet type.
Trichet type, no. I mean, no, it's used mostly for other spaces because it's not interesting to embed to L infinity. So it's also useful for L1 and L2 spaces. In general, L3 spaces. So let me recall the definition of the space L1, and I will use it in the following slightly non-standard. I'll use a slightly non-standard definition. So a space of L1 is a family of random variables, and the distance between two variables c and eta is equal to the expectation of the absolute value of the distance.
Why not?
So, and what is distance? What is this?
So the distance between two.
These are the
Random
real
variables
values.
with real values, yeah.
A real value. Okay.
Yeah. Yeah.
It's abbreviated.
Real random variables.
I mean, are you to the 2, right?
And the
Real values, random variables. Are these squared?
huh?
Are these squared? For
No,
sure.
no, no,
Yeah, I agree.
it's not that. It's,
Okay, yeah.
Okay.
Yeah. There was an
It
attempt
was a
to make a joke, but some of you
Did
failed.
succeed.
Yeah. In producing and understanding it, yeah.
so, and this space of one is very actually useful in computer science, and I'll show this after I do this theorem. You could run routine. Every metric space on endpoint embed into L1 with distortion log n. And here I also don't specify the exact concept. So I could,
But you don't say anything about the dimension, L1 on how many points?
yeah, I don't. So
And could you please also write down the year of the theorem?
I think it's 1984.
Oh, recent.
No,
I was born this year.
compared to,
One of the oldest theorems in this area.
but Frechet is much older, I guess.
For sure,
Yeah,
much
yeah.
older,
Well,
beginning of the
one.
20th century.
After Frechet only.
So I will prove only this theorem. In fact, so you can the number of dimensions you can be log n, or like big O of log n. And in fact, true for all LP spaces, so it's not necessarily L1. And it can be L2 or any other LP space. And this log n is in fact a tight bound, so you can compose this log n in general.
Yury, I'm again confused because, so what means L of omega? Omega stays for 4.
For the
what?
For the random space. For the but
But in that theorem, this is the same L of omega or not?
yeah,
Yeah, of course, L1 is depends on the set measure space with measure, where you consider these functions.
Okay, and
So-
omega is that space.
Omega is
Yeah.
that space, and here we do not say anything. It may be even an infinite space, or whatever.
So for some omega.
For some omega.
for some omega. So I don't want to pay attention to this space. So in fact, you can always take L1 is 0, 1.